Greetings everyone. I've been following Bruno VK's YouTube channel for quite some time, and one of his latest videos was part 11 of the Don Smith spin-off experiment series. And I had the parts on hand and thought I'd give it a shot, so was just going to provide the video back to show some appreciation, Bruno, for all the work that you've done and the documentation and experiments. That you're not alone, and there are those of us that do appreciate it and are following along with you. Anyways, let's get into a little bit more of what's the setup is going to be. So Bruno posted this schematic, and I have a very similar setup. This is the gate driver, of course, from Rick, going through the L1 of the coil you were just staring at, and I've tuned mine down to match the secondary L2 and L3 coils that I have. Everything's tuned for about the 639 kilohertz range, just because of the components and coils I had on hand. How I'm measuring everything so far, I found that it seems to work better if I use a sensing coil. Just at the very edge of this is, I don't remember the microhenry or millihenry rating of it right this minute, but it's an air core that's just sitting right on the edge of this thing at 90 degrees, and have my oscilloscope ground and primary going back, and that allows me to isolate my oscilloscope from the main tank circuit. So I seem to get better results consistently, higher voltage gains, and just more accurate readings in general. The rest of the circuit is all fed from just one of these little signal generators. You can see it's tuned to our current resonant frequency of the main L1 coil. Square wave sitting at about 50%, I think it's 48 to 50% duty cycle. Power is just being fed in from the wall currently. The signal generator is just 5 volts, so it could run off battery or USB port if necessary. This is a DC to DC converter, so basically it's my version of a little small, easy, adjustable bench power supply. It's fed 12 volts in from wall wart or a power brick. Feeding out, it's variable. You can control voltage and current independently, so depending on what you're looking for. Feeding into the gate driver, and of course the grounds between the DC and the signal are both tied together here at the gate driver. And that pretty well sums up how my setup is currently configured. Okay, now that we've talked about the primary setup on the L1, let's talk about the secondary side, where the opposing coils, counterclockwise and clockwise coils with the bridge rectifier, and what Bruno did with the two coils, or two capacitors, separated but in parallel. So my setup today, it's definitely not ideal nor exact compared to what Bruno was doing, but it is similar. It's the best that I could do it at this time. I don't recall the windings amount that I've done on here, the winding amount. It was a long time ago in another project, but it is one layer all the way down, and then about a third of the way back. And the reason I did it that way is to get in a specific width of the coil, so like sliding inside of your L1 it would match appropriately, and I needed a specific length of wire for testing wavelength at the time. But that was different. I'm just explaining what's in this setup. They're wound on PVC pipe, but there's a smaller one that's been sanded down that's inside these two pipes. They're independent, and they can slide on top of that internal PVC right here, so you can adjust it once you slide it inside the L1, and you can actually adjust L2 and L3's distance from each other, because looking at the testing, it actually makes a difference how far one side or the other is in and what relation they have to each other as well. This is our little tuning cap right here. I think it's 100 picofarad silver mica. That's pretty much what I've used with these. They seem to work better in these radio frequency ranges and get higher voltages consistently and stable and don't want to blow up, things of that nature. So this one is, for the record, I forgot to mention that this one is clockwise and this coil is counterclockwise. The ends are connected to the bridge rectifier and of course the plus and minus side, the tops of the coils. Tops going over to this side of the bridge rectifier, top, or the bottom of this coil, but the top end, because our L1's in the center, so voltage going out, just like our Tesla coils, goes out to the edges. This one's going into the other side of the AC side of the bridge rectifier. And then our capacitors, which are 1 kilovolt, don't remember the brand, or I don't know if there's a brand, but these are 0.33 microfarad, 1 kilovolt rating. They do, and on some other experiments, just testing AV plugs, like coming off the negative side of the coil, from Rick Friedrich's book. Just doing simple tests with that. You gain voltage rapidly with these coils, and you have to be, or capacitors, and you have to be very careful. These diodes are 1N4148, high-speed switching. They're very, I think, 100 volt rating, 200 milliamp. The milliamp rating is, I've seen them go well over 100 volts. I have no idea if it's good for them, probably not, but they seem to handle it all right. But they, with these capacitors and these diodes, they make an excellent combination when, in far as the testing goes, that I've experienced. I've used the silicone diodes and some other high-speed switching diodes, and these seemingly, in practice, seem to be the better ones for me. I'm not telling anybody else what to use, but that just in my practice, these seem to work better for me. I can routinely get 140 volts on this capacitor within just a second or so off the negative side of that L1 coil with 12 volts input, just in a tank. Just once you finally hit its natural oscillation, I think 880 kilohertz, something like that. But that's pretty well the wrap up. So outside the coils, bridge rectifier on both sides, centers are tied together right there, and then of course top and bottom here is this little tuning capacitor to put this one into a to resonate at the 639 some odd kilohertz we're looking for. So and the grounds of these two are tied together, and I've had fairly inconsequential results with actually tying a ground into this common ground here. It doesn't seem to affect it much one way or the other, maybe just a few millivolts. Alright, this should be, oh, the loads. Also, the loads are seemingly very important, just like Rick has always specified. We'll be using two in this demonstration. This little RV bulb is a 12 volt bulb. Let's see if I can get this thing to focus. It's just a row of, I'm pretty sure they're series LEDs, little pads at the bottom. It has a built-in full bridge rectifier, a little smoothing cap. I think it has a voltage regulator. I haven't actually looked up that part number, but I believe that's a voltage regulator. I could be wrong. It might be some kind of different IC to buck boost. I'm not sure yet, but I know it'll regulate its voltage pretty decently. But they work effectively well. You can You can put positive or negative to either post. It doesn't really matter. It'll take AC, and they seem to work adequately at these higher frequencies as well. You'll get a response out of them. And then the other is just some regular bead diodes. They're soldered together in series just for demonstration. I want to say there's our part number. I don't know, I got a 50 pack of these from China for like $2, so they're good for blowing out and testing things. Good for loads that you don't want to put at risk. If you lose a couple, it's not a big deal. So anyways, that's the basic general setup. So next phase we'll show this actually put slid together and functioning. Okay, here we are running with the L1 coil. It's churning along at 13 volts output on the DC converter, about 40 milliamps. Keep the gate driver within tolerance that way. It's yeah, it's just barely above room temperature. The sensing coil is picking up about 400 millivolts. So that's about optimal tuned for this L1 coil. So now if we add in the, so as you see, the LED that's connected right here, like Bruno set up across positive to this side of the LED to this capacitor, excuse me, positive on this side, negative on this side, then the common ground, or if you connect it. But as you see, I get a response even without a ground. So as we slide it through, you can see your waveform drop off. Let's see if I can tune it about right, and there. Seems to be one of the better performances. It's still about 300 millivolts, so it doesn't really detune your main tank, and you can adjust the frequency a little bit, and it doesn't really get any higher. It stays about right there, so your magnetic field pulsing doesn't increase any past that. Your LED's lit pretty adequately. You can't really tell with some of these lights I have, so you can, for the lighting for the camera, so you can see what I'm working on. So it kind of makes that look pretty wimpy. It's pretty decent lighting. I wouldn't light a room with it, but you know, just flashlight quality, it's pretty decent. But you can see I've already pre-adjusted the two coils to be their optimal distance away from each other, expanded or away from each other, and now I was just sliding it in and out. But you can see that there's quite a bit of gap between the two coils, even though they're electrically connected. And you can increase still the sine, or the sine wave. It's higher in resonance, but there's no LED being lit. There's no power on it. So you have to find that optimal sweet spot, which is just outside, and it can work on both sides. You'll notice it work on both coils as well, which I've got the camera going, so of course it's not going to function right, but it will work on either side. But this right side, or this right coil, seems to be a little bit better, and I say a little bit, it's marginal, just a few millivolts. But I don't know if you can, if this is coming through on the camera or not, but this coil right here is almost, it's completely out and about an inch away from the outside edge of this coil, of the L1. It's hanging way out here. This one is almost completely in this L1, or inside of it, but not quite totally. Doing some testing earlier, I noticed that there was a and most people probably know this, and it just escaped me. This is a complete learning process for me. I'm no engineer, so this is just a learning process, and people may take things for granted, information they know that others don't. But while I was taking my sensing coil and setting frequencies, I noticed that there was a peak here and a peak there, but they were out of phase, or they were opposites. So, and right in the middle, there's a dead spot. Most of the time, it's pretty close to the middle. So I'm gonna equate that or assume that that's very similar to a blotch wall, like in a permanent magnet. Have like a north pole here and a south pole there, and then you've got this dead blotch wall right in the center. So that's kind of what I was thinking with these two coils, that you're being off. They're not right in the center. If you get in the center, you don't get much output at all. But if you offset it or have an asymmetrical setup, like we've heard over and over, it does seem to give you, that's where your power seems to show up. Yeah, it just has to be offset just a little and asymmetrical. And I'm not sure if this is what Don Smith was talking about with you had to unwind. One of the top coils of the L2 and L3 was 50 turns, the other was 52 turns, or whichever way it was. I don't remember off the top of my head, but there were just a slight difference. And I'm wondering if that was very similar to what he was talking about, is setting up that imbalance to take place so you can produce power. So keep in mind that's without a ground connected. Oh, that's interesting. Probably a loose wire somewhere in there. But anyways, let's move on to some of the loads as well. The interesting part about the loads. Okay, on to the load testing part. Put a multimeter over here. Connected it to our positive and negative side. I know this is high frequency RF, so that's probably not entirely accurate, but it's pretty close. You can power this thing off and it sits there at that voltage for a couple seconds and drops down. So it, I think it's pretty accurate overall. Something to keep in mind this whole time, by the way, if we pull this coil out, our input goes up to 40 milliamps. Once we put the coil back in and tune it to the optimal spot, it actually drops down. Wow. I don't know if you can see that or not, but it's about 20 milliamps. So with the load, I know if anybody follows Rick and his stuff with the motors, that's pretty common and not that unheard of for him. The interesting part that I found on this was it's definitely load specific. You can see that there's 8.32 or 23 volts on here. If I disconnect this just for a second, that thing will climb rapidly to, you see it's almost instant, 95 volts. Try not to do that without blowing out these bulbs, but as soon as you put a load on it, it loads it down. I'm sure there's some capacitance voodoo and some calculations that I'm missing on this, since I just kind of picked these at random because they worked well and not really sizing the capacitors, and I'm still learning through all this, in other words. Here's another one. So we're going to take these other, see if we can get it in frame here. These other LEDs light up about 3.5 volts a piece, like most LEDs. So we're going to put them right here in parallel with the other ones. Nothing. Still at 3.22 volts. So in parallel on the bridge rectifier and the capacitors, no light whatsoever. You can disconnect this primary one and makes a liar out of me. Why are you making it? I might have this hooked up backwards. Let's try that again. I forget that those don't have a rectifier on them, so they do get, only go one way. So, but the example is still valid, as in when this one's plugged up, these don't light. You unplug it, those light up. Not terribly bright, but you see the effect. Also, if you'll notice, voltage went up. Less of a load, they went farther up. But the part that I really found interesting was, if you, let's see if I can remember which way to connect this, is if you're connecting them in series. Let's see here. Not that side. Let's try this one. Haha. So they're both equally as bright as they were before, or relative, I mean within just a small margin of error. By the way, our input over here on the DC converter has not changed at all. It's still 13.10 volts input and it's 10 milliamps, so it actually went down just a few milliamps. That's got about a 5 to 10 milliamp range, so I think it goes in 5 milliamp intervals. I don't depend on it too much. But notice your input voltage. That, or not input, your capacitor voltage now on this meter, 18 volts. Wavelength hasn't really, let's see if I can retune this edge just a touch. There we go, get it climbing up to where it should be. Anyway, so both LEDs in series now, in parallel they would not run whatsoever. In fact, it was just one or the other. As soon as you run them in series, boom, they run just fine. So another demonstration to show your loads are very important. However you load this system, series is definitely the more beneficial, seemingly. The only other thing that I noticed that was rather unusual with this whole setup, and it wasn't really with this, I was just happened to stumble on it while I was doing this experiment, and that was let's see here. Yes, I was hooking up the negative side of this. So you've got your positive of the gate driver going into the 100 picofarad cap in series into this one. Then it's got some tank caps to make it resonate. Then it's just the negative out to the gate driver. But it's all connected to the DC, and the grounds are all connected together. But I was hooking this ground up to, or the negative side, to a ground. Let me see if I can get one to demonstrate. So we have a ground wire, which this is just grid power right here coming out. And in fact, this is the DC power brick for that DC converter. So I just clip my clip lead, very dangerous, please don't try this at home, to the negative side, not the neutral side, but the ground plug, the safety ground plug right there, and ran it down, back this out just a touch, to right here. And this is that negative right there. And when I connect the ground to that negative side, see if I can get where I'm trying to explain here. Notice what your milliamps do. They zero out. Now, there again, I don't really trust this thing that much. It's not that accurate. It's just a DC to DC step up, step down, $6 one off Amazon. It's not a super. It's reliable, but it's not necessarily super accurate. And I'm sure the grounds are tied together. So that got me curious, because there's still power flowing through it, because there's still some heat on the little gate driver. It's not terrible, but it's just a little bit, just above room temperature. Speaking of which, all our loads are still running just like they're supposed to. No variance there. It didn't dim it, didn't brighten it, didn't do anything. So we zeroed out that. So I actually, we're going to snag this multimeter real quick, because it's got other ones but not handy. So we're going to use it. I was curious because I'm like, well, surely this thing's not that accurate. So let's try to put a actual amp meter on there as well, in line. I forget what you call these. It's a DC amp meter. It's a clip-on, but just Hall effect. So it's showing 50 8 milliamps right now. So I mean, you still have the LCD powered up, and the electronics inside it are still humming along. So you're using power, but you notice that it jumps up on the negative side, of course, is what we're measuring. The positive doesn't seem to have an effect, so maybe electrical engineers, I'm sure, will have answers and explanations for that. But nonetheless, I was thinking, well, maybe that just has something to do with tying back to the common ground, and either way, it does fall from both meters. And I took it a step further and actually put a battery and powered this from a battery, and it did. I connected that ground back to the negative side of the battery, and it did the exact same thing. So the DC converter was completely isolated on a battery, powering it up at 12 volts, and its milliamp draw just dropped to, it zeroed out. So maybe that's feeding that's shuttling the power back around, as we've kind of been looking for. But I'm sure there's probably a mathematical error and a measurement error, since I'm still learning, that I'm just missing here, and that's usually how it goes. I end up discovering it, and nonetheless, it's interesting. I don't know if it spurs a thought for somebody else, but hopefully so. Anyways, just a overall experiment to maybe it helps some people, and just to express to Bruno that we appreciate it, or I do anyways. I'm sure I'm not alone, but I know that I appreciate his experiments, and keeps me motivated to keep trying and keep testing new things on my side as well. So thank you, and I hope you all have a good day.